Welcome back to the last video for TEC 240 on Wednesday, January 13th. In this video, we're going to get you all set up and ready to do Lab 1. So to do that, first we're going to review how to add resistors in series and in parallel. And then we'll actually take a look at Lab 1 and step through Lab 1 and the instructions for how you should do Lab 1. So let's go ahead and switch over to the document camera. Okay, here we go. And I'm going to draw some stuff. Never thought that I would be playing around with jumbo-sized markers in my job, but it makes it a lot easier for you to see compared to if I just did this in pen. So let's say that we have we're only talking about resistances here, so I'm not even going to draw a voltage source. Let's say that we have a circuit in series, and we have this resistor, which we'll call R1, and let's say this one is equal to 100 ohms, and then we have an R2, and let's just keep it easy and say this is 200 ohms, and then we have an R3, equals 300 ohms. Like I said, let's keep it easy. All right, so you probably remember that for a series circuit, to calculate our total, the total resistance for the whole circuit, all we have to do is add them up. It's real easy. So in general, I'm just writing out the equation in general variables right now. So we have R1 plus R2 plus R3. And if we had more, we'd just keep on adding them. So I'm going to write it like this, plus dot, 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 plus R in, where in is however many resistors we have in series. So now I'm going to plug in numbers. In this case, our total equals R1, which is 100 ohms, plus R2, which is 200 ohms, plus R3, which is 300 ohms. And I might even be able to do this math in my head. 100 plus 200 is 300, 300 plus 300 is 600 ohms. So our total resistance in this series circuit is 600 ohms. All right, that is pretty easy. Okay, now let's move on to a parallel circuit. And you might remember their equation from TEC 111. In a parallel circuit, let's draw it first. So here is our circuit, and let's say we have R1. Let's even keep the same values. R1 equals 100 ohms, and R2 equals 200 ohms. And R3 equals 300 ohms. All right, how do we know that's in parallel? Well, it's pretty obvious here, but you might get some more complicated circuits where it's not quite so obvious. But in general, the way you can tell that it's in parallel is if the current has a choice to go through this branch or this branch or this branch. If I had a power supply right here, which would provide our electromotive force to push charge through the circuit, then the current has a choice to either go, assuming the positive side of the voltage source is on this side, the negative side is down here, then it would push current, conventional current, through this side of the circuit, and then if we anthropomorphize, it's a big word, anthropomorphize the current, then we could say that the current has a choice to go through this branch or through this branch or through this branch. In a series circuit, that's not true. In a series circuit, the current doesn't have a choice. It has to go through all three of them. So we know these are in parallel because whatever current goes through R1 has to also go through R2, and whatever current goes through R2 has to also go through R3. If the current doesn't have a choice like that, then they're in series. if the current can choose which path to take, then they're in parallel. That's a good way of thinking about it. All right, now we'll write our equation. Our equation for parallel, this is the part that often people forget. It's not R total equals, it's 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. The most common way I see people messing this up is that they say R total equals 1 over R1 plus 1 over R2 plus 1 over R3. That is not true. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so now let's just do the algebra and then plug it in. So 1 over R total equals 1 over 100 ohms plus 1 over 200 ohms plus 1 over 300 ohms. All right, so now I'm going to have to plug that into my calculator. So I'm going to have 1 over R total. And then I'm not sure if you're going to be able to see these digits. You might actually. So I'm going to use parentheses 1 divided by 100 in parentheses plus parentheses 1 divided by 200 in parentheses plus parentheses 1 divided by 300 in parentheses. And I get 0.0183 repeating. This is 0.0183 repeating. That gives us 1 over R total. We don't want 1 over R total, we want R total. So the way you do that is by taking the inverse of both sides. So what I'm really doing here, I'm taking 1 divided by both sides. What you do to one side, you got to do to the other side. So what I'm doing here, I'm going to go over here so I have room. What I'm doing is 1 divided by 1 over R total equals 0.0183, but remember I have to take 1 divided by both sides. Okay? Now the reason I want to do that, and that looks more complicated than what we had before, but actually it's not. Because if you remember a rule of algebra, if you have something in the denominator of the denominator, it's actually in the numerator. Okay? That sounds complicated, but it's really not. Here's the proof. If I have 1 divided by 1/2, okay? How many times does 1/2 go into 1? How many halves are in 1? 2, right? And 2 is in the denominator of the denominator, so actually you can move it up to the numerator. It's just 2, okay? So when we have 1 over R total, what we actually have is R total. That's just a little trick of algebra. So this is equal to R total. R total equals 1 divided by 0.0183 repeating. So all I have to do is take 1 divided by that answer, and I get 54.5 ohms. R total equals 54.5 ohms. Okay. All right. What you will notice is that the value of the total resistance is always going to be less than the value of the smallest resistor. You will always know that, which is a very convenient way to check your work. If you're doing lab 1 or on the exam or whatever, and you calculating the total resistance of a parallel resistance network, your total resistance always, always, always needs to be less than, should be less than, the smallest resistor in the parallel network. If it's not, you did something wrong. Conversely, in series, you'll notice that the value of the total resistance always, always, always needs to be, should be larger than the largest resistance in the resistance network. Okay, so again, that's kind of just kind of a dummy check where if that's not true, then you did something wrong. Let me do a couple more examples There's one more thing. Yeah, let me do two more things. Won't take too long. Let's see. What should I do first? Let's. This will come up. Yeah, I'll do the one that is directly applicable to Lab 1, and then we'll talk about something else. All right, so it won't always be quite as simple as you got 3 resistors, calculate the total resistance. I could give you something like this. Let's see, I'm going to just make up numbers here, so I hope they work out. Let's say, I'm literally just making up numbers here. Let's say this is going to be 80 ohms. I'm telling you, our total is 80 ohms, and R1, let's say R1 is equal to 500 ohms, and let's say R2 is equal to 300 ohms, and let's say we don't know the value of R3. So the question is, what is R3? This will come up in Lab 1, and this is the most common question in Lab 1. It's pretty common, actually. All right, so there's really nothing different here. We got to solve the exact same equation as we had before. We've just switched what's known and what's unknown. So our general equation is still 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. And now we can plug stuff in, but just be careful where you plug it in. So our total is now 80 ohms. So what we've got is 1 over 80 ohms equals 1 over R1, which is 1 over 500 ohms. 1 over R2. R2 is 300 ohms. R3, we don't know. So let's just call it R3. If you want to call it X, that's fine too, but I'd prefer just to call it R3. All right, so when we're solving an algebra equation and we've got one equation and one unknown, we can solve it. And the easiest way to solve it is get all the unknowns on one side and get all the knowns on the other side. So I can't do anything with this term yet. Eventually I'm going to get R3, but for right now, this term, I can get that whole thing by itself on one side. These are just knowns, they're numbers. So combine all the knowns on one side and combine all the unknowns on one side. So what I'm going to do is I'm going to subtract this term from both sides, and I'm going to subtract this term from both sides. So what I'm going to end up with is 1 over 80 ohms minus 1 over 500 ohms minus 1 over 300 ohms equals 1 over R3. All right, so now we've got something that looks really quite similar. There's subtraction there instead of addition, but this is starting to look really similar to what we had right here, right? So it's really not that much of a stretch, but it does cause problems for students, which is why I'm doing this right now. Okay, so now we can just do this math. And so what do we got? We got, let me clear everything. We've got parentheses 1 divided by 80 in parentheses minus parentheses 1 divided by 500 end parentheses minus parentheses 1 divided by 300 end parentheses. So that gives us 0.00716 repeating. So I've got 0.00716 repeating equals 1 over R3. Don't forget, you still got the 1 over R3 here. Okay. This brings up a good question that often comes up. How many sig figs should you have? All right, so in the middle of a problem, as you're going through the problem, you should keep quite a few sig figs. you should keep at least 5 or 6 sig figs in the middle of the problem as you're going through the problem. When you get your final answer, that's when you can do some rounding. Quite honestly, when you're working with resistance values, you do not have to go to a fraction of an ohm because we can't even manufacture a resistor to that tight of a tolerance. So rounding to the nearest ohm is perfectly acceptable when you get to the final answer. So let's do that. Let's keep, I've got 5 or 6 sig figs here, and I'll keep that for now, and then when I get to the final answer, I'll round to the nearest ohm. That's what I want to do. All right, so once again, to solve this, I want to know R3, not 1 over R3. So what we got to do is take the inverse of both sides. And last time I wrote it out where we took 1 over what we were trying to find equals 1 over the value that we had calculated. Another way of writing that same thing that you will see in lab 1 is to take a negative exponent, -1. If you raise something to the -1, like that, all that means is you're taking the inverse of both sides, 1 divided by whatever you had there. So this is the same thing as writing 1 over 0.00716 equals 1 over R3. Okay, so when we have 1 over R3, that just is R3. If you have something in the denominator of the denominator, it's actually in the numerator. So all we have to do here is take 1 divided by what we had, and that gives us 139.53 ohms. But like I said, let's round to the nearest ohm. So we're going to round up here to 140 ohms. Equals 140 ohms. Because we can't even manufacture a resistor that is 139.53488 ohms. That's preposterous. All right, so don't forget your units. And now we know that R3 equals 140 ohms. That actually worked out pretty well. I had to be careful with the values that I selected here because it's possible I could end up with something that is just completely wacky. If you ever end up with a resistance value that is negative, you did something wrong, because there is never let me say this, in practical life, there is never a time when you would end up with a resistance value of 0. If you're in a lab somewhere or working with superconductors, then okay. If it's really, really, really cold, then you could end up with exotic materials with a resistance value of 0 ohms. In the real world, which is 99.99999% of the time, you will always get a resistance value that is greater than 0, usually at least a couple ohms. Even a section of wire has a couple of ohms resistance. All right, so you will see that on lab 1. Let me go ahead and do one more thing that you won't see on lab 1, but you will see on lab coming up. I don't know if on lab 2, but definitely on lab 3. So let's say you have a resistance network. I'll just do a kind of simple one so that you get the idea. Let's say that you've got R1 equals 100 ohms. And now let's say you've got R2 equals 200 ohms. But now it's not quite so simple, because now you've also got this resistor here. Let's call this R3. We'll say that's 300 ohms. And we've also got this resistor here, which is 400 ohms. All right, so you won't see this in lab 1, but you definitely will see this in the coming labs next week. So what do we got here? We need to analyze this. So take a look at this. Well, we've got R1 and R3 are in series. How do I know they're in series? Because whatever current goes through R1 has no choice but to go through R3. It has to. Also, whatever current goes through R2 has no choice but to go through R4. So R1 is in series with R3, and R2 is in series with R4. but this branch is in parallel with this branch. How do I know that? Because the current, as it comes here, it has a choice. This is a node, actually. We'll talk more about nodes in coming labs, but when it gets to this node, it has a choice. Does the current want to go through here? Yes, some of it will. Does the current want to go through here? Yes, some of it will. The only question is what proportion of it will go through this branch and what proportion will go through this branch. And we'll do that later, but for now, let's just calculate the resistance value for R total. All right, so for now, the question is just, what is R total? All right, so here's what you can do. What I'm going to do is use different colors. So what I'm going to go ahead and do is combine these resistors into another resistor that I'm going to call R. I'm going to call this R equivalent 1, R sub EQ1. And I'm going to combine these resistors, into what I'm going to call R equivalent 2, R sub EQ2. And now what I can do is I can redraw this circuit, but simplified. And this is R EQ1, R equivalent 1, which is not a real resistor. This just represents the combination of these two resistors. All right, and I can do this math in my head. R1 and R3 in series is 100 ohms plus 300 ohms. So R equivalent 1 is equal to 400 ohms. And then I can draw R equivalent 2. And again, I can do this in my head. 200 ohms plus 400 ohms gives me 600 ohms. All right, so now I've simplified the circuit into something that I actually can do with the equations that we just talked about. This is our total. We know that 1 over R total equals 1 over R equivalent. Let me go ahead and write it out just because it's a little bit different. 1 over R equivalent 1 plus 1 over R equivalent 2. Now I'm going to plug in values. 1 over R total equals 1 over 400 ohms plus 1 over 600 ohms. And now, in fact, I'm going to add those up, but I'm going to go ahead and write this out. I'm going to take the inverse of that. I'm going to take the inverse of that, which just means 1 over this amount. All right, so first do what's inside the parentheses. So I've got 1 divided by 400 plus 1 divided by 600. All right, that's what's inside the parentheses. And that gives me that number. Let me go ahead and write this out just to make it clear. I don't want to skip over too many steps here. All right, so I've got this 1 over R total inverse equals 0.00416 repeating. And I'm taking the inverse of that, okay? So now it should be pretty obvious, I think, that the inverse of 1 over R total equals 1 over R total, which is the same as R total. And now all we have to do is take the inverse of this. So I take 1 divided by that, and I get 239.999999-ish, which is 240 ohms. All right, so now I can go back up there if I wanted to, and I could say, now I know that R total up here equals 240 ohms. Okay. All right, that's a good example of how you're going to have to solve circuit problems in the coming labs where it's more complicated than just something like this or like this. It's going to be pretty easy in lab 1. We're going to indoctrinate you slowly, but pretty soon you're going to be solving circuits like that and even more complicated than that. So I want to give you a little preview here. If you don't understand that, you know, watch the video as many times as it takes, but definitely if you don't understand it, after watching it a couple of times, get in touch with me and let me know, and I'd be more than happy to go through it with you in more detail. Here's lab 1. So this is what you need to do after watching the video today. You should be able to do it with Tinkercad and with your calculations that you know how to do. So what I want to point out is that anytime it says the word calculate, and let's see, is it not, it's not on page 1 of the lab, but anytime it says the word calculate, you're going to actually do the calculations with your computer or a calculator. Anytime it says the word measure, that means Tinkercad. So do this in Tinkercad. Anywhere on this lab you see the word measure, that means put it in Tinkercad and actually measure it. This might seem kind of silly. What I'm telling you to measure is measure the resistance in Tinkercad of a resistor that you set at 560 ohms. Obviously, it's going to be 560 ohms right here, all right? It's not a trick question. If we were in the real world, a 560 ohm resistor might not be exactly 560 ohms. It might be 559, or it could even be 555 or something like that. There's a tolerance that resistors are manufactured to. But in Tinkercad, it's going to be exact. All right. So it's not a trick question, but do it. I'm trying to work you into Tinkercad slowly so that you get the hang of it. Okay, so build this circuit in Tinkercad, measure it, measure this circuit. For this circuit, you want to put this in Tinkercad and measure it. Also calculate it. They're in series, so you know how to do that. And these are in parallel, so build it in Tinkercad and measure it in Tinkercad. Down here, I want you to build this parallel circuit and then measure it in Tinkercad. And this is basically the last thing in Tinkercad. Okay, number 9 in lab 1 is the last thing in Tinkercad for lab 1. So this is what I want you to take a screenshot of. Once you build this circuit in Tinkercad, take your screenshot, make sure that your file name is visible with your last name space lab 1, and then include that in the upload with lab 1 on RegNet. Okay, save as last name space lab 1. Okay. The rest of everything is calculations and a few short answer. All right, so oh, you know what? Actually, I was wrong. I did not read this carefully enough. Okay, so actually, I was hasty when I went through this, and you know what? That's fine. Just this, you can include the screenshot of this, but I do want you to measure this as well. Okay, so actually, this is the last thing that you're going to do in Tinkercad. Sorry for the lack of clarity there. All right, so that's actually the last thing that you do. Quite honestly, if you want to include a screenshot of that one, that's fine too. I just want to see that you know how to do this in Tinkercad. So quite honestly, if you include the screenshot of this one or this one, it's fine. I just want to see that you know how to do it and that you did it. Okay. All right. Also, I want to clarify, because this could definitely be a question. On page 7, this is part of lab 1. So you need to do this and include this page in your upload. So this is part of lab 1, but you do not need to put it in Tinkercad because it just says calculations. Okay, so don't, I mean, it's good practice. If you want to put these in Tinkercad and then compare your measured results in Tinkercad compared to your calculations, that would tell you if you did it right. but you don't have to. All right, just take a scan of this page and this page and this page, and also add your JPEG of your screenshot, and then you're gonna upload that in RegNet. All right, so that's it for Lab 1. Also, don't forget that there is a quiz, the very first quiz, and it's pretty easy. It's pretty straightforward. That quiz, the first quiz of the semester, is due on Sunday, January 17th by 11:55 p.m. So that pretty much wraps up the first week of Tech 240. If you have any questions about anything that we've covered this week, don't hesitate to reach out and ask. I'm here for you, and I'm happy to help, so let me know how I can help. Otherwise, have a great weekend, and I'll see you next week.